Hi scholars, welcome to this presentation on incorporating statistical analyses in conducting multiple baseline design studies. On the screen right now is a design that you should recognize as multiple baseline design. There are 3 participants, and so this is a multiple baseline design replicated across participants. You'll notice there's continuous data collection in the baseline phase. There's this staggered introduction of the intervention, and what we've done so far in the course is analyze data through visual analysis. So as an interventionist, when you're implementing this study and collecting data, you're continually graphing so that you can do the visual analysis to see the participant's response. And then you make decisions about when to intervene based on what you see in terms of level, trend, variability. So here, Amir's data is relatively stable. If I were intervening and just using visual analysis, I might say, I've got enough data. I don't need to keep collecting. It's fine to go ahead and intervene. But what actually happened in this set of data that we collected is we incorporated 2 levels of randomization. And the reason we did that is because we really wanted to see, is it perhaps just chance that there's change in behavior, or is it possible to say that there truly is some sort of effect happening with this intervention that we've implemented? So the first level of randomization that we did is fairly simple. We took all participants' names, put them in a hat, pulled out the first name, and that first name was Amir. He was our first participant to begin the intervention without replacing his name. The second name we pulled out was Nadia's. She was the second tier participant here, and finally Moyed was the third tier participant. So we randomized order of participants, and then we used this expert software package that I'll share in this video to randomize the intervention start point. So we put in a range of dates. We knew that we wanted at least 3 data points, so somewhere between 3 and 7, we were going to begin the intervention for Amir, and we let the randomizer decide that. At the same time that we made that call, we put in the range of possible dates for Nadia and range of possible dates for Moyed. And then we began collecting data, knowing when these intervention start points were going to come up for the other students. We were able to communicate that information to teachers and parents. That kind of helped in coping with this really long wait that happens when you have this delayed intervention, and some students are maybe languishing in baseline. So there was that advantage to it, but the big drawback could be, there's no do-overs in randomization. So what might have happened with this study had we seen this accelerating trend in baseline for Amir, or an accelerating trend for Nadia, that might have skunked the whole study, but that's part of randomization and part of what we're after when we're evaluating effectiveness of an intervention here. So the contents of this presentation in part come from the work of Dr. Joel Levin, and I'm going to highlight that expert package and show you where you can find that. It's freely available. There's other software packages that are available, but because the one that I'm going to show is fairly easy to navigate and free of charge, I think it's worth calling our attention to in this class. I'd like to credit the work of Dr. Joel Levin, and then a student of his, Boris Bufarov from George Mason University, has helped with running updates on the website and software package to continually make it better as more users make use of this platform for analyzing data. It is free, and it's also worth noting that more commonly, when you submit for a potential publication, the manuscript using on a study for single case research, reviewers are accepting and expecting that you'll incorporate some randomization into the design. So we're focused really only on multiple baseline designs and using some within case and between case tests. What you see on the screen here looks like an Excel spreadsheet. This is a set of data to show 3 tiers of participants, and each row for row 2, 3, and 4 is a participant's data. So I'm not necessarily sure what the intervention was here, but I know that participant 1 has a 4 on the first session, a 3 on the second, and a 5 on the third session. The researcher here has used yellow highlight so that session 2 and 3 indicate the potential start dates for when that participant would move from the A phase to the B phase. Row 3, the second participant on session 5 and 6, the 2 dates are highlighted. And then the final participant 3, sessions 8 and 9 are highlighted as possible start dates. So you can see that there would be this potential stagger of when the intervention might begin if we were to plot this data as a set of stacked line graphs. So on the screen now is a view that you get when you use the expert software package. So we're putting in the potential for the intervention start points, kind of populating data from what you just saw on the previous slide, and then setting our probability level to, in this case, 0.05. It's open if you wanted to run a 0.01 significance level. When you click run, then you get the cells to populate to tell you when to intervene and intervene. And when you have all of your data to graph, the software gives you these visual displays of data that are not APA formatted, and so it's helpful to see this depicted here, but know that you would still have to recreate the graphs to make them APA formatted. But it will also generate data about each case in terms of an effect size, and then uses the NAP, the non-overlap of all pairs, to give a overall effect across participants here. So expert focuses on that non-overlap of all pairs. It's fairly easy to understand. It's straightforward to compute that. It's done automatically through this expert software, but you can also calculate by hand when you have a small number of participants and fewer data points per participant. So I'm going to show what NAP actually is, and let you know that typically when you compute NAP, we cite in Social Sciences Parker and Vanest's work on non-overlap of all pairs. It's done automatically through the software. There are singlecase.org calculators where you can calculate online accurately. You can use SAS or R or SPSS. You can use a Mann-Whitney U-test. But if you have a small number of participants, the gist of what you're doing is you're finding the total of paired comparisons across phases. You do that by figuring out the number of points in the baseline phase multiplied by the number of points in the treatment phase. Then you find this overlap zone, and I'm just going to advance ahead to show you the overlap zone here, are the dotted lines that span across A and B. And within that zone, only pairs that show decline and ties are counted. Then these decline and tie pairs are subtracted from the total number of pairs to get the POS. This is the formula that we use to calculate NAP then. And so it's relatively simple to execute that by hand, but you can also use one of the online calculators for NAP. So I'm going to link on the Canvas website the the Weebly site for expert. And I know I just showed a couple screen grabs of it here. If you are thinking about conducting a multiple baseline design, then I can walk you through it, although the directions that are included on that site are fairly user friendly. But I just wanted to point out that this is freely available and is a possible way to evaluate data. If you're looking at other studies and other designs, I'll touch base with you during our Zoom meeting to figure out other ways that you might use randomization in your studies.